Hey there, YouTubers! Hi there, Dr. Sheep here. Welcome back to another chemistry video. Today is another video in my series on the periodic table. To get yourself up to speed, make sure you watch the first part of my series. For those of you that are still with me, today we're going to be talking about the first column on the periodic table, the alkali metals. Here's a note to teachers showing this to their classes. I will be covering topics like quantum mechanics and relativity. So I'm sorry if that causes people to have more questions that you probably won't be able to answer. I do have videos on those topics. My DAE on the 200 mile per hour fastball, my momentum video, and my energy series all are good resources to explain those answers. And all of those can be found on my channel in playlists. So if you go there, you'll find them. Consider subscribing so you don't miss a future video on the periodic table and physics. The alkali metals consist of the elements lithium, sodium, potassium, rubidium, cesium, and francium. All of these metals have one valence electron. Each of them want to get rid of that one electron, and as the mass of the atom increases, the more willing that atom is to get rid of that electron. Lithium is still very reactive, but it's the least reactive of the section. Each of these elements, when dropped in water, release hydrogen. However, every element heavier than sodium explodes. Coincidentally, every element heavier than sodium melts when it reacts with water. The reaction between water and sodium happens so fast the elements become very hot. Each of these elements have relatively low melting points, which is why they melt. The melting points get lower as the elements get heavier. Lithium has a melting point of 180 degrees Celsius, sodium at 97.79 degrees, potassium at 63.5 degrees, rubidium at 39.3 degrees, cesium at 28.44 degrees, and lastly francium at 27. Just for reference, those last three would melt at on really hot summer's days, provided you live in an area that can get hotter than 40 degrees Celsius or 100 degrees Fahrenheit. I just so happen to live in one of those places. Gallium is a metal that's not in this section, but is a metal that can melt at relatively close to room temperatures. And YouTubers have made a lot of videos on it back when it was trendy. It melts at 29.76 degrees Celsius, which is higher than cesium or francium. I just wanted to mention it because I would have paid good money to watch YouTubers play around with it, play around with cesium. But that would be right before their hands would be blown off, and I don't want to see that because that's yucky. Whew. This looks complicated. These are atomic radii here. I didn't label that, but whatever. As I stated before, as the alkali metals get heavier, the more violent the explosion you get when they drop in water. Each explosion is much greater than the previous one, so logically, francium would make an explosion that would dwarf cesium. This isn't the case though. It turns out, according to the YouTube channel Periodic Videos, they said that the electrons going around the atom of francium are going at speeds of a fraction the speed of light. Before I move forward, I feel like I need to mention quantum mechanics here. You see, electrons do and don't go around the atom. To understand that, watch my energy series and the previous video in this series. If the electrons are going around at speeds close to the speed of light, that means relativity plays a role. According to relativity, as an object's speed increases and approaches the speed of light, the mass of the object increases. This is due to a variable most people don't even know exists, and Albert Einstein's famous equation, E equals mc squared. The variable is gamma. For today, all you need to know that is the reason for the increase in the mass of the electrons. To learn more about gamma, watch my 200 mile per hour fastball video and my momentum video. That increase in mass causes the electrons to get closer to the nucleus than you would expect. When the electrons are closer to the nucleus, the protons are able to pull on them more. The result is the atom is less likely to give those electrons away, and thus a less reactive francium. Okay, stop! I can hear you screaming at me through the camera. You're asking me to show you these reactions in real life. So, here's lithium reacting with water, which has been a part of my intro since the refresh of my channel. So this is a chunk of lithium. You've seen it in my intros. When it gets dumped in water, it reacts and creates hydrogen. Oh wow. Now at the time of this recording, I don't have any sodium metal. However, it is on its way and is supposed to be here on the 15th of January. It is currently the 6th. So I should have some footage before this goes up. If not, here's an awkward cut. Alright folks, it's time for the sodium. I decided to do this in 2 scenes, but here it is. 10 grams. So each of those cubes would be 5 grams. We're going to cut the 1 cube in half and then cut that in half, which would be about 1.25 grams. I just hope we have enough distance. Do not try this at home or anywhere, for that matter. So yeah, see you out there. 3, 2, 1. Three. Okay, so I don't have any other alkali metals because they get really expensive. But I have some footage from a fellow YouTuber called Cody's Lab, so make sure you check him out and share some love. So here's some footage from his 1 million subscriber special where he makes a cesium metal YouTube play button. I will only show his footage with his permission. If he didn't get back to me between now and when this goes out, here's an awkward cut again.
3, 2, 1.
Another problem as the alkali metals get heavier, they don't necessarily produce a larger explosion. Cody's Lab brought this to the forefront of my mind again after I watched his play button video. Even though the atoms react faster, that doesn't mean the explosion is bigger. Roughly the same amount of energy is being released each time, gram for gram. I had forgotten about this because I have been reading about the elements, not actually handling them or watching videos. Note to future me editing, make sure you add the Jimmy Neutron style after talking about salt. And then also at the very end, show a clip of the sodium hydroxide and aluminum reaction. So it's all fun and games throwing these alkali metals into a lake besides the pollution. But is there any real world use for them? Great question. The book, The Elements, a visual exploration of every known atom in the universe, is a great read and provides examples of these elements in the real world. Lithium is used in batteries that power your smartphones and Elon Musk's cars. Lithium carbonate is useful for controlling mood swings in people with mental disorders. Sodium, when reacted with chlorine, produces sodium chloride, or ordinary table salt.
You said sodium chloride. Yes, it's the same as salt, but you could have just said salt instead. Everyone in this town knows you're a boy genius, dude. You don't need to say overly large words to sound more intelligent. The fact of the matter is that nobody cares how smart you are. If anything, calling simplistic objects by their scientific name ironically makes you seem less intelligent and more pompous. I know you're smart enough to be better than this.
that you use on your food almost every day. Sodium hydroxide, or lye, which I used in my video to make soap, is useful for soap making. Duh. Sodium hydroxide in a solution with water will clean your drain. Or if you add aluminum metal, it will produce hydrogen gas, which is explosive and flammable. Potassium is useful in fertilizer as potassium carbonate. Potassium is also found in bananas and is a valuable micronutrient to us. Also, most samples of potassium are slightly radioactive because 1/100th of 1%.
When the top 1/10 of 1%, not 1%, 1/10 of 1% owns almost as much wealth as the bottom 90%
of potassium on Earth is potassium-40, a radioactive isotope. Don't worry though, potassium-40 is accounted for in the background radiation here on Earth. Background radiation is the baseline level of radiation in the environment here on Earth. Rubidium doesn't actually have a lot of applications other than some fireworks to produce a purple flame, or in rubidium clocks, which worked similar to cesium clocks. Cesium, or more specifically cesium-133, is used only to keep time. The second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between two hyperfine levels of the ground state of cesium, of the cesium-133 atom. Wow, thank you, Theodore Gray. That was a lot, but that is the definition. Lastly, francium has no real-world uses. It doesn't have a half-life long enough. Don't know what a half-life is? Check out the last video. The longest half-life is only 22 minutes, and that's francium-223. And the only way to gain enough francium to study is to make it in a lab. Wow, that's another periodic table video done and dusted and in the bag. Join me another 2 weeks to talk about the alkali earth metals. But in the meantime, I'd like to thank you all for watching. Please like, comment, share, and subscribe. New videos every other Friday, 2 p.m. Central Time, and good night. Subs for trees, subs for trees, subs for trees, subs for trees. Oh, you're still here? I thought I told you to go home. Oh, you want more? I'm flattered. Check out the playlist. If you want exclusive content, check out my Instagram, Dr_sheep_YouTube. That's all lowercase. If you want to help the earth, subscribe. When I reach 100 subscribers, I'm going to plant 10 trees. If you feel that's too small, then check out my channel chart where I lay out even bigger goals. Finally, stick around for the next 20 seconds to give me that sweet watch time. Bye.